mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Hey, welcome back to grade 12 physics, my class. I hope you're having a good day today. Hope things are going well for you in your homes and that you are able to get these lessons and that you're able to do the assignments. And I just want to tell you that hopefully you're learning some things as well. I've been learning some things as I've done this online video stuff now for a couple of days. I've learned that I don't like it very much. I don't like teaching to an empty classroom. I miss our daily interactions. I miss you guys, and I miss the way we interact with one another as I teach. I don't have to tell Jordan to take his hat off, or I don't have to tell Colby to take his hat off. I don't have to worry about people coming in late. I won't name names there. You know who you are. And yeah, I just miss that. I've learned a couple other things. I've learned that having this big white board behind me makes my ears look really big. I don't like it. I don't know what it is, but it makes them look very big. I've also noticed that there's a nice big glare off the top of my head. Not sure I like that either. And I've also noticed that I don't like watching myself on video. And especially when I turn around and face the board, that bald spot on the back of my head is bigger than I thought it was. And when did that happen? I don't know. Anyways, I wanted to let you know that I put a solution manual to our textbook on Connect, and so as you get questions that are out of the textbook, you can find the solution manual and the solutions to those questions online. It is a fairly long document, it's a big book, and so you have to find the chapter that we're in. And so right now in our book, I'm actually not even sure what chapter we're in off the top of my head, but find the chapter, find the page number that we're on, and then the numbers will correspond, and you'll be able to find the answer. Now just be aware that the way the textbook does some questions is different than the way I do them, and it doesn't matter which way you do the questions, but the answers should be the same. So get down to the bottom of it, find the answer, and see if it matches yours or not. And if you have questions, make sure you email me your questions, and I can either respond to them by email or I can address them in the next day's video. And so you can do it that way. All right, yesterday did have a couple of questions on yesterday's assignment. Really just one question. It was on questions 3 and 4. It's the same question, same kind of question, and the response to them is the same. And so I've done question 3 on the board behind me here. Let's just take a look at it. You've got the question there in front of you, hopefully, or you can get it in front of you, so I didn't write it down. But we've got a baseball that has a mass of 0.250 kilograms, moving with a speed of 40 meters per second, caught by a back catcher whose glove moves back 0.25 meters as he's bringing the ball to stop. And the question asks a bunch of questions about the kinetic energy of the ball, about how much work the catcher did, and what the net force acting on it is. Now, the first part, A and B, are pretty simple. Work is force times, work is change in kinetic energy. So, anyways, stop. A, kinetic energy. EK equals 1/2 mv squared. You've got the mass, you've got the velocity. Okay, 1/2 times 0.250 times 40 squared, and you get your kinetic energy. Part B says, what's the work done? Well, work is change in kinetic energy. And so it is going from that kinetic energy that you just found in A to a kinetic energy of 0 as the ball is stopping. And so you're going to get a negative amount of work. When you do 0 minus the number, you'll get a negative amount of work. And again, that just simply tells you that the force that's acting on the ball is opposite to the direction the ball is going, right? Slowing the ball down has to be in the opposite direction, and that's what the negative sign tells you. Now, part C says, what's the average stopping distance? Well, to find that, we set up our formula. Work, FD, equals change in kinetic energy. Final kinetic energy minus initial kinetic energy. Divide both sides by the displacement, and you get this formula. F equals 1/2 mv2 squared minus 1/2 mv1 squared over d. Plug in your numbers, and the numbers that were given in the question. again, recognizing that this first part, the kinetic energy, finally is 0 because the ball comes to rest, minus the initial, and again, you have those numbers from the previous questions, over the displacement, and you get a number. When you just do the math, you get a number of negative 8.0 times 10 to the 2 newtons, and it's negative again because that force is in the opposite direction that the ball is moving. The ball will be one way, the force has to act the other direction in order to make it stop. Question 4 is exactly the same. It asks you to calculate the force that is slowing the bullet down as it enters the block, and it asks for you in 2 ways. It says, what is the force of the block on the bullet? And that's going to be a negative force because the block is slowing down the bullet. The bullet is moving in, the force has to act the other way. The final part there says, what's the average force of the bullet on the wood? And that's going to be a positive one. Again, that's an equal and opposite reaction. That is Newton's third law, where if we have a force slowing it down, a force on the bullet is also applying a force on the wood, and they're equal and opposite. So that's how those questions work. Continue to ask questions. I will continue to try to answer them. Hopefully this answered that question. You know what I'm also realizing? I just learned something. I learned that I write on an angle. I will have to try to fix that up. All right, let's get into today's lesson. Today's lesson, we're going to start looking at potential energy. And again, energy is the ability to affect change on our surroundings. And we talked about kinetic energy yesterday and how when we have something that's moving, it has kinetic energy and it can do work on other objects. Now today we want to look at potential energy, starting potential energy. And there are a bunch of different kinds of potential energy. In this course, we're going to focus on 2 different types. And the first type we'll start today is called elastic potential energy. Now, elastic potential energy has to do with anything that has elastic properties. So we're looking at things like springs. And I've got a few springs here. Here's a spring. It's a really long one, but we can stretch it. And when I stretch it out, as it's held here, it has the ability to do work, because as soon as I let go, it's going to return back to its original shape, and that has the ability to do work on something. It has to do with things like balls that you can squish, and then they return back to their original shape. That has elastic energy. When I compress it, it now has stored energy, and when I release it, it has the ability to do work on an object. All right, and so a scientist by the name of Robert Hooke did some work in elastics and elastic energy, and he came up with a law. He was credited with a law. And again, physical laws don't explain things. They just kind of state the obvious almost, and then it's up to the math to then explain it. And so Hooke's law simply said this, and it's not shocking. It says the amount of deformation, okay, the amount of stretch, the amount of squeeze, whatever it is, of an elastic object is proportional to the force applied to deform it. Now that should make complete sense, right? The amount of deformation, so the amount this spring stretches, is directly proportional to how much force I use to stretch it, right? That is not rocket science. If we apply more force, it will deform more. Same as with the squishy ball. I can squeeze it lightly, a little bit of deformation. I can squeeze it a lot, get a lot of deformation, and those 2 things are directly proportional to one another. If we were to graph it, we'd get a graph like this. We have force on our vertical axis. We have x, which is the amount of stretch. It's a distance. It's measured in meters. Force is obviously measured in newtons. We'll get a graph that looks like this. We get a nice straight line. It's a linear graph. They are nicely, it's directly proportional, and we get a nice straight line on it. Now, I've got 2 points marked off on here because this line doesn't stay straight forever. It goes straight for a long time, and then it hits a point where it curves and flattens out, okay? And that's with all springs. The point where this starts curving is called the elastic limit. It's the point at which you have stretched a spring or you've deformed something to the point where it no longer will return to its original shape. And if you do that, you get slinkies that look like this, that no longer go back to their original shape. No matter what I do, this will not return to its original shape. Somebody has overstretched this slinky and it no longer returns. So it has been stretched beyond its elastic limit. All right. We have a second point here, that's called the breaking point. If you stretch something too far, eventually it will break. Really hard to do with springs, but elastic bands, you do this all the time with elastic bands, right? You can stretch them, stretch them, stretch them, stretch them, and all of a sudden they break, all right? And so that's the breaking point. So this graph has to reflect that all elastic objects have these properties. As we apply force, it'll stretch more and more and more, or compress more and more and more, until it hits an elastic limit. That elastic limit is the point at which it no longer returns to its original shape. It is permanently stretched or compressed. And then eventually, if you keep stretching it, it will eventually break, and you will no longer have any elastic potential energy. All right, as I said, force is proportional to the distance that something is stretched. The more it's going to stretch or compress, we're going to have more force. And as with all things, we find the slope of this straight line. Okay, that will allow us to convert this to an equation where we get F equals Kx, where K is the spring constant. The spring constant is a number that is specific to the elastic object. So various springs have different K's to them. All right, so a slinky, for instance, would have a K that is fairly, I don't know, it would just be a number that would represent how much force is required to stretch this. The spring in this little scale is a spring in there. Again, this is a much stronger one, so as I pull this one, okay, there's a spring in there. It's got its own constant. The springs in your vehicle that allow you to absorb those bounces, those are fairly strong spring and have their own constant. So every spring has its own constant, and the constant is in newtons per meter. And this is our formula for the day, F equals Kx. All the questions you're going to do today revolve around F equals Kx. Now, we're going to end it there today. I'm going to give you a couple questions that just deal with F equals Kx and be fairly straightforward. Normally, if we were in a classroom setting, I would probably continue on and give you the next section as well. But because we're doing this online learning, I'm going to save that and do that tomorrow. The next section involves converting that potential energy into kinetic energy and back and forth. And to do that, we're going to have to learn about the conservation of energy. And so we'll do that tomorrow, and how we can create a situation where we have potential energy, and then as we, for instance, if we compress a spring with something on it, and then we let go of it, it's going to shoot that thing off with a kinetic energy. And so we're going to look at that and see how that works. But for today, we're going to do this. The assignment today is going to be a handout. It's going to be 4 questions that you will find in a PDF in the handouts section of Connect. And again, if you have any questions, please feel free to ask, and I will answer them. They should be fairly straightforward. Again, the answers on those papers are on the paper themselves in brackets at the end of the questions. Okay, so as we end today, I just want to remind you that we have a verse of the day, and our verse of the day today comes from 2 Corinthians 9, verse 7, where it says, "Each of you should give what you have decided to give in your heart, not reluctantly or under compulsion, for God loves a cheerful giver." Have a great day. Remember to subscribe to the YouTube channel so you can have easy access to these videos. And have a great day, and hopefully things are going well for you at home, and hopefully we'll see you tomorrow.